That's fine. Come on. This time. Good morning, everyone. My name is Daniel Nagasawa. I'm a second-year graduate student at Texas A&M University. I'm very happy to be presenting some of my work regarding the chemical abundance analysis of several ultra-faint dwarfs discovered in the Dark Energy Survey. Now, the Dark Energy Survey has been in operations for the past 5 years. In fact, this is their 5th year of observations right now. And in the first 2 years of observations, the Dark Energy Survey discovered 22 candidate satellite galaxies to the Milky Way. Now, discovery is not the end of science. Now we want to move on to characterization. And there's an ongoing effort by many people in the community to characterize ultra-faint dwarfs chemically. So I'm using high-resolution spectroscopy on resolved stellar populations to determine element abundances for a couple of member stars in these ultra-faint dwarfs. And once a chemical abundance pattern has been measured, then I can kind of compare that to nucleosynthetic models in order to determine what the nucleosynthetic history of the universe was, because these objects actually preserve a very interesting fossil record of the early nucleosynthesis in the universe. Now, here at this conference, I'll be presenting on one particular object, Horologium-1, which presents an unusually low alpha element abundance for its metallicity, which is explained by a couple of scenarios, which I'd be happy to talk to you at length, but I think I'm about out of time. So thank you very much, and come see my poster. Yeah, from here? Okay, let's skip that. Okay.
Hi everyone, I'm Drea Karelia and I work with Charter Jogi here at UT. And we study the spatially resolved star formation histories of nearby spirals using Vanga IFU survey. Vanga has high spatial resolution, a few hundred parsecs compared to kiloparsecs for other IFU surveys. It covers red to blue wavelengths with medium spectral resolution, and it has coverage from the central regions to the outer disk. And this allows us to study in great detail how spiral galaxies assemble, and more specifically how the different components, the bulge, the bar, and the disk, assemble their stellar populations, like the different age in stellar, metallicities, distributions, star formation history, star formation rate, specific star formation, and whatnot. So here I have some sample galaxies. Here's NGC 2903, the H-alpha flux map and total stellar flux map. And I have indicated here, which you probably couldn't see, the size of our fiber. So for all of those fibers, we have a spectra, and we can feed it into our stellar population synthesis and get star formation history. So for example, like for this plot over here, it's a mass fraction distribution of ages and metallicities, and you can kind of see, this is also just preliminary, you can see the different episodes of star formation, and we're looking into, yeah, okay, sorry about that. Yeah, come talk to me. Hi everybody, my name is Jackie Champagne. I'm a grad student here at UT. I am working with Caitlin Casey. So along with Caitlin as well as Charling, we've been looking at this cluster, this overdensity of dusty star-forming galaxies and Lyman break galaxies. And because they span a very narrow redshift range of about delta Z of 0.02, we've declared this a rapidly star-forming protocluster. So these are SCUBA-2 selected sources, and we are looking at CO1 to 0, so we have follow-up JVLA observations to try to characterize the molecular gas, and therefore the potential for continued star formation in this protocluster. So this image here, this is a background near IR image, and then the contours are showing these CO1 to 0 detections. So along with some of the previously identified galaxies, we have a number of serendipitous CO detections in this protocluster, which is really awesome. So here I just have a moment zero map of one of these particular sources and its corresponding spectrum. But the reason that this protocluster is particularly interesting is that a paper from last year by Wang et al. Published the same pointing along with an extended X-ray source, and they used that to argue for a hot intracluster medium and therefore a fully virialized cluster. But because this is at redshift 2.47, that is a huge claim, right? That would be the highest redshift virialized cluster to date. So in my poster, we discuss alternative scenarios for that, so come talk to me.
Hi, I'm Guang Yang from Penn State. I work with Dr. Neil Brand on the supermassive black hole and galactical evolution. So we also study what's the most important factor of host galaxies related to the black hole growth. What we found is that black hole crashing is related to the stellar mass quite strongly. The dependence on the star formation rate is weak, which means that if you look at a very massive galaxies, we will have higher accretion rate. We have published our results. We have our new results. We further studied the black hole accretion, stellar mass relation, and its redshift evolution in detail. Is present in this figure. You will find that at high mass galaxies, the black hole accretion is really a strong function of redshift. It's the distant universe is very different from the local universe. But at low mass, the evolution is weaker. So that's it. Thank you.
Hi, my name is Taylor Hutchison. I'm from Texas A&M. I work with Casey Popovich. I'm going to be talking today about near-infrared spectroscopy galaxies during ionization, specifically measuring their carbon-3 emission, because even though Lyman alpha is the most robust tracer for high redshift galaxies, carbon-3 gives the systemic or true redshift, and it's not attenuated by neutral hydrogen within the epoch of ionization. Specifically today, I'll be focusing on work from one of our primary galaxy, which was spectroscopically confirmed for Lyman alpha in 2013 by Steve Finkelstein and UT. Over here on the left is the H-band spectra for many years, including a recent observer run back in April, and the Y-band spectra for Lyman alpha is beneath it. And then on the right-hand side is our co-added Wendy spectrum. If you want to talk about this, or my analysis, or anything, come find me at my poster.
Good morning, everyone. My name is Jonathan Flores. I'm a student here at UT working with Sharda Jogi. And we are exploring galaxy growth as a function of environment during the important epoch of redshift 2 to 4, during which the cosmic star formation rate density and AGN activity peaked, and protoclusters began to collapse. We're doing this with the Sheila Headdex dataset, and this dataset offers unprecedented advantages for studying galaxy evolution during this epoch for several reasons. For one, it will be targeted, or it is being targeted by several photometric surveys that range in wavelength from UV and optical to the far infrared, and it will also have Headdex optical spectroscopy. And two, it will be probing a large co-moving volume, so we're going to have data for a large range of galaxy environments, as well as rare high-mass galaxies. And we will have data for roughly about 0.8 million galaxies. So right now we're restricted to photometric redshifts, so we want to determine how accurately we can measure galaxy environment using our current photometric redshift estimate. And as an example, I show this figure from my poster where I calculate the correlation function of a mock catalog, for mock catalog galaxies, some illustrious mock catalogs, and I introduce photometric redshift uncertainty. All right.
My name is Yin-Tai Chang, graduate students in UT working with Steve Finkelstein. I'm doing kind of a spectroscopic search for Lyman alpha emitters at the end of reionization. Sure. So the amount of neutral hydrogen may affect the property of observed Lyman alpha features. And in theory, the higher amount of neutral hydrogen in the integrating medium may the steeper slope for the equivalent to its distribution. So to constrain that equivalent to its distribution of Lyman alpha emission, we can perform the Lyman alpha spectroscopic search, and by simulating the expected number of detections in our data set, we are able to find some kind of best fit for the shape of equivalent to its distribution, which is kind of key property to study the amount of neutral hydrogen in the integrating medium. So to study more, just come to find me in the poster room. Yeah, that's it.
Hello, my name is Logan Pierce. I'm working with Dr. Kraus here at the University of Texas. I'm an undergraduate student. And my research project is on the orbits of long-period exoplanets. So directly image planet surveys have uncovered or discovered a class of substellar companions that are extremely massive and on very wide separations from their stars, which is a parameter space that's not well accounted for by planet and star formation models. So my work has been to precisely measure their positions in infrared images from Keck Observatory and use that to try to constrain the orbits, allow the orbits of observation to try to look for clues in the allowed orbits toward their formation mechanism. And so if you'd like to learn more, please come to my cluster.
Hi, my name is Richard Seifert. I'm working with Chaoling Hung and Caitlin Casey here at UT, and my research is on trying to understand the formation of galaxy clusters by looking at the gas instead of at the stars. So when we look at galaxy clusters today, they're mostly made of red elliptical galaxies, and there's not much ongoing star formation. But we see a lot of stars as well, so that means that at some point in their history, there must have been intense star formation. Gas probably plays a big role because gas is the fuel star formation, so by looking at gas, or gas in the cluster of progenitors, I'm trying to understand how they formed. And yeah, that's it. Come to my cluster.
Okay, good morning. I'm Sofia Rojas, and I'm an undergraduate here. I've been working with Steve Finkelstein and one of his grad students, Matt Stevens. And my project is about finding some of the most distant galaxies in the universe at redshift about 8 to 10. And to do this, we're using the Hubble Space Telescope, and we're using the brightest of reionizing galaxies survey. So this is a survey that is using pure parallel imaging from the telescope. Basically, it means that it's looking at the same time that the telescope is looking at another primary target. So we have the advantage of looking at random spots all over the sky to find these galaxies. And here you can see some of the galaxies that we've already found at redshift about 9. And the way we're doing this is using the photometric redshift technique, where we are looking for the Lyman break, and we drop out the filters, and then we see where the galaxy is actually looking at. So if you would like to know more about my research, please come talk to me. Thank you.
Thanks everyone. So